So let's dive now right into the practical testing tips. So the first one is don't skip measuring your capacitance and dielectric loss. Whether you're doing that with the LCR meter, if your dielectric loss is low in the range of 0.2%, or with your impedance analyzer, either utilizing the phase to calculate dielectric loss. Don't skip this step. It's important. It provides another data point for analysis, and it is relevant as we discussed in session 1. Repeat measurements here in relevant conditions. What I mean by repeat measurements is when we start our piezoelectric ultrasonic device assembly, we start with the bare crystal. So do your resonance and capacitance measurements there. The next step we do is we bond our piezo to, or we assemble our device. We bond or assemble, and you need to do measurements at this time in fact as well. Then we also, if there are also any subcomponents, we do in between the assembly, we also would provide and do measurements in that case. Sometimes there's attachable tools like a needle for ultrasound. For surgical devices, or a needle or a scalpel, or in welding there are also other tools that you add to your ultrasonic device in order to provide actuation. In the case of an ultrasonic cleaner, especially in the case of Langevin transducer, we assemble the transducer separately and then we bond or weld the transducer then to the structure. So in each of these cases represents a unique physical configuration, and each of those physical configurations you'll want to perform tests again to recharacterize that. And this kind of goes to the final point. Let me jump here because it may seem like there's so many measurements to do. There are, and it's gonna be a lot of handwriting unless you automate those measurements. I don't recommend skipping steps here because a common occurrence in ultrasonic transducers development is that we encounter an issue, we want to look backward, but we were missing data. So if you automate measurements, you spend time taking more measurements. If that's not possible, spending more time in that, it will save you time in the future. The next is to perform fixture calibration. That's also just to understand as well what the impedance of your fixture is to begin with. You don't want a fixture with a series resistance of 100 ohms. You don't want a fixture with 5 nanofarads or 3 nanofarads of parallel capacitance. So you should actually measure your fixture just to understand where you lie. If you need to actually optimize that, because you don't want to calibrate to very large extents if you can avoid it. But nonetheless, providing and using fixture calibration will lead to better results. Pay attention to measurement speed. And what I mean by measurement speed is sweep speed. So when you perform an impedance analysis, there's a sweep which happens. In my case, I can insert a delay time, or we can specify frequency steps in order to change how fast the measurements are taken. But this has a very large effect on measurements. If you do your measurement within 1 second or 45 seconds across the resonance and anti-resonance regions, you have to find that sweet spot that's not too long, not too short. Something 30 seconds and larger for a high Q material, a Q factor above 200 is important to do a larger sweep time. Basically, do a design of experiments. Create a grid of different impedance analyzer settings, and understand which settings lead to stable, accurate results. So design of experiments, we typically think about that in the assembly process, or in the bonding, the epoxy, or when we are using finite element analysis, we look at the optimization of the crystal size, or what's the optimum size for the metal component. But looking at it also from a equipment standpoint, because there are many settings and they will lead to different results. So you can use a perfectly calibrated top of the line equipment but get incorrect results, or you can use something more custom and get relevant data as well. So it just kind of depends on understanding your tool to the highest extent. So using calibration and the fact that you have an expensive equipment doesn't always relate to correct results. The next portion is to check the accuracy with passive components. So you can use a capacitor and a resistor to measure and ensure that within your measurement range that you're looking for, that you are getting correct readings for resistance and capacitance. Resistance comes with a much higher tolerance. You can get them very accurate. Capacitance don't have such good tolerance, but at least if you purchase a low loss capacitor and high frequency stable like a film capacitor, you'll be able to get a general idea that your measurements are correct, as well as you can determine the phase angle. The phase angle should be very low, considering the low loss capacitor. You can use a ceramic capacitor, for example. So pay attention to other resonant modes. So there's always that single resonant mode that actually represents the operating mode, but there are other resonance frequencies occurring, and these, as we showed in FE8, are characteristic of other properties and other phenomenon in the material. So in the transducer. So they can also reveal changes in these factors can also reveal a better understanding of behavior and performance. This goes along with this fact that use the results in conjunction with finite element analysis. If you notice, so use these results in conjunction with finite element analysis to better understand what your data is telling and what it's signifying. Take more measurements rather than less. So all of the measurements and that I outlined in the summary parameters are very important to characterize. Whether you're directly able to use them for analysis or making engineering decisions today, perhaps and very likely tomorrow, what will happen is there may be a failure or a new design requirement, and adjusting your current transducer, you may not have the data in order to support that work, especially statistical data. So taking more measurements rather than less. Automation is important here. Also, when you're doing your frequency sweep, use as many points as possible. Typically, I've seen either 1,000 or 1,600 points permissible in your frequency sweep. Use all of them. I think 1,601 is the limit on some of them I've seen. The one I was using doesn't have a limit because it's a custom setup. In addition to taking more measurements rather than less, record the raw data, the screenshot of the impedance, and also record the summary parameters so you can quickly and easily compare. So you'll have all of the data needed, and you don't have to kind of dig back in if you want to do additional analysis or look for a spurious mode, or you are wondering if these harmonics had a difference, and you had taken some of this good advice and you had measured this frequency range, although you weren't sure quite what to make of it at the time. You dug back in, let's say, at a point of failure to the FEA analysis, and you realize these modes can be used to determine the quality of an assembly or a specific failure point that exists. So establish repeats of measurements sequentially and over time. So best practice is, at least whenever you do a measurement, you measure that parameter 3 times. You take an impedance analysis 3 times, as well as over time. So after you do system testing, which uses higher voltage, you may see changes in your device performance, perhaps degradation or changing of resonant frequency. So doing these measurements over time helps you understand degradation and change in performance over time, especially if your device has has significant assembly steps which do affect performance. You will have over time changes in performance as the ceramic and the interfaces wear in. In this slide, I'm going to give a brief overview of high power testing of ultrasonic transducers. So the impedance analyzer works at 1 volt, and it can only provide low power. So even if you had a 1 ohm resonance impedance, you will not be able to provide 1 amp from your impedance analyzer. The trade-off here, and by using low voltage and low power, you get an extreme amount of consistency, and that is where this device shines, and it's why it's a basic analysis parameter, because in order to do better characterization, we need to obey and follow linearities. But actual applications work at 10 or hundreds of volts, and they also use higher power in terms of watts or tens or hundreds of watts. What happens in higher power is we get large oscillation, so the displacement is very large, and this creates nonlinearity. We also get heating, which additionally changes properties. So with increased displacement or increased stress and strain in our piezoceramic and our transducer, we have 3 phenomena happening. We have the quality factor decreasing. We do have the coupling factor increasing, but that's not I think that's not the most significant effect. The most significant is the quality factor decreases and the resonance frequency decreases as well, so the material gets softer. What also happens at this frequency, due to large shifts in oscillation, when you get to the resonant frequency, because as we described, let's say this is displacement. As we get to our resonant frequency, let's say it's sweeping upward, we have a large displacement, right? But what actually happens is if you are, let's say, sweeping downward, so you're starting from a high frequency, you're going down in frequency. So as you're reducing in frequency, the resonance frequency starts to shift. So what happens is that you get a nonlinear behavior as the resonant frequency shifts. As you get closer to the resonance, it also reduces. Eventually, you do hit the resonant point, and right after you hit the resonant point, you get a nonlinear jump downward as the oscillation suddenly decreases. Your resonant frequency suddenly increases again as your oscillation level decreases, and that creates a nonlinear event. That also happens, and it provides challenges to high power measurement. The most simple way at this point to understand high power testing and is to use what you should do is, one, you can implement your system level test, system testing with power measurement. And kind of very quickly, voltage times current, if you have voltage and current waveforms, and you take the average of those waveforms, the DC average, you'll end up getting the power. So you take that over about 10 to 20 cycles, and you will be able to get the average power dissipated. And you also look at your system tests, whether you're measuring your displacement in microns or you're measuring an acoustic radiation force or or equivalent power or welding capability. That's going to be the 2 factors that you can use to correlate a power measurement as well as in a system level test. The other way, which we won't describe here, is doing impedance analysis, but doing it under a constant power frequency sweep. So by using constant power frequency sweep, which has to be done with closed loop control, that will provide the linearity, the control of power delivered. It'll control the linearity needed to perform impedance analysis using the methods I described in these lectures. However, system testing is effective, but this is why and impedance analysis at high power isn't a standard, isn't available commercially in a standardized format. Therefore, the impedance analyzer becomes very valuable for that reason. And using system testings along with electrical measurements during system testings can help fill the gap of understanding high power tests. So as a review of these 4 sessions, we have capacitance and dielectric loss. Capacitance has both intrinsic and electromechanical contributions. And dielectric loss is mostly from the electromechanical contributions. It also can signify how a material is bonded. And it also describes losses occurring in low frequency operation, and they can be better described and understood where those losses are coming from finite element analysis. But it's mainly you can get crystal property information from dielectric loss. The mechanical and electrical resonance in session 2, we learned about those 2 factors. And additionally, we learned about electromechanical resonance. We spoke about the 1D example and also the distributed systems. And because everything in the real world is distributed, and that's taken advantage of in ultrasonic transducers, nodal points and specific frequencies, it's critical to understand also how anti-resonance happens, how we have this parallel capacitor, how that then affects and creates anti-resonance, which isn't particularly a mechanical phenomenon, but exists electrically, which can be confusing. But I think it provided a great example about assuming the charge generation black box we spoke about in session 2. In session 3, we spoke about equivalent circuit. How do you calculate that? Now getting into practical calculations and summary parameters. Distilling all this information down to a key number of parameters that we can use to compare devices. I went over in the 4th session practical measurements of bending and longitudinal Langevin type transducers, as well as a crystal measurement of a crystal. There were some practical comments and also calculations done there. And here, I'm providing a summary as well as high power measurement, a short discussion on high power measurement. So here are the topics for additional study. There is high power resonance characterization, the characterization of piezoelectric material properties from piezoresonators, also the displacement and velocity measurements, as well as finite element analysis of ultrasonic transducers. All of these are going to be kind of valid next steps in this discussion.